quickly. If I have already interviewed you, please don't share the questions with anyone. Don't share what you got on the homework with anyone. During the interview, the kind of question that I ask you, you can expect them to appear on your final exam. So those were my way of checking your knowledge and give you pointers where you don't know something and need to study it. So you might see a body plot on final exam and I ask you questions about that. Same as I will ask you on your interview. So a couple of you are left, so I'm not going to spoil the questions. Next week is a still game. So I will teach. Last day of classes, Monday, 25th, is going to be exam review. Optional if you want to come in, ask questions. If not, I will still record it. You can watch the video. I know it's going to be closer to study day and capstone craziness. So if you wanted to stay in the lab and watch a video or do later, up to you. I'll come in, talk about kind of question, and then that's it. All right. So hopefully next week we will talk about the state space, which is the last part of this class. All right. Any questions on those? So there will be a final exam, all right? Which actually is good. It's going to hopefully help your grade. All right. We had a few things left from last class on lead lag design using frequency domain, basically a body plot. Before I go to those, I thought that I'll talk to you about no, class on 25th is not on Zoom. You're either in person or you watch the recording, okay? Because I might let him to take a day off. Because he's been working hard. I think he deserves one day off. I cannot control everything just by myself. So before we go to lead lag design, I want to piggyback on body plot because based on my interviews, the knowledge on body plot is not on par with S domain and time domain. My assumption is that you're busier, you didn't study much, you don't follow the lectures, that's why. So, but I think if I connect S domain to frequency domain, that would help you a lot because I assume everyone is pretty good on S domain, all right? Let's say we have a transfer function of, so our loop transfer function is G times GC, which is the controller. So when we say loop transfer function, that's what we mean, what I mean. So this is your plant, this is your controller. If this was your feedback loop, this is the loop transfer function, right? So it's very specifically, if I said loop transfer function, I mean controller and plant together. If I said system, it's just a plant. You need to design the controller. Now, this means that we've designed the controller already. We're just looking at the control and plant together. We're not doing the whole feedback thing ourselves. Body plot usually looks at the open loop, right? It looks at the system and controller itself. Now, for a loop transfer function, GS times GC, 50 over a second order, find the break frequency. What are break frequency? I think I never discussed what they are, but this is where we can connect S domain and frequency domain. Break frequencies are the frequencies that your poles will happen at those frequencies. Okay, now, what are the poles of this system? How do you find them? Like, I will tell you what they are. What are the poles of 50 over S squared plus 12S plus 20? What do you do to find poles? I assume everyone knows that. Nobody wants to talk about it. Equal to 0, S negative 2, and negative 10. So you have two poles at these 2 points. You remember S is J omega. So it's the frequency basically. So since these are real, only real parts, so we know that these two will happen on real axes. So at omega equal to negative 2 and negative 10, those are actually our poles. We also call them break frequency. The reason is that if you plotted body plot by hand, you had to plot the asymptote first. where the asymptote cross each other, there are the breakpoints. So let's say this is the asymptote here, this is the asymptote here, and for this one, that's the asymptote, something like that. This phase, you can do the same thing from the other domain as well. Phase is a lot easier. Now, if I plotted this like more realistically, these would have been here. I did -2, let's say. It will cut here. So -2 and 10, -10. So the omegas are positive value because these are just real numbers, so right? So this would be, so these are the poles, but these are the omega, 2 radian per second, 10 radian per second. All right. Now, if we pick a pole at the origin, where would that frequency be on the body plot? Where would that pole be represented on the frequency domain? For S equal to 0. I expect you to tell me. Frequency 0 radian per second. Let's say this is logarithmic, so I don't actually know where 0 is. So let's say omega 0 is here. So means that the gain related to that pole, the phase related to that pole are there, or there exists a pole, for example, here if it was at the origin. Okay, so this is how we connect the position of pole and 0 to our body plot. Now, you see that you're going from 10 to 0, getting closer to your imaginary axis. So moving toward imaginary axis is almost as we are going toward here, because this is like negative infinity, like well, you're going not negative infinity. Actually, this is not omega 0. Omega 0 is somewhere here that we don't reach. You don't have it right now. So this is 0.1, right? So as we go this side, we get closer to 0 radian per second. Here is just large omegas. Higher frequency, lower frequency, imaginary axis, and as the frequency goes higher. Now, if this was only on the real axis, now if you are like somewhere that have imaginary and real part, you have some number plus j omega, then again, that omega is your frequency. Does that make sense? So it is important for you to understand that how body plot is connected to S domain. What was the plot we used in S domain to tell us about the stability of the system? You could see different values of pole for all the gains. Root locus. So if you are in S domain, you look at root locus. If you're in frequency domain, or you want something in frequency domain, look at body plot. If you want to see the behavior in time domain, you look at step response or ramp response, right? You get something from each of them. And they have to match, because if you're plotting them for the same system, they have to match. This was not 0, right? This is like whatever number between there. So 10 to the power 0 is 1. So this one is omega equal to 1 radian per second. So I'm just showing you how it progresses. All right. So if you wanted to draw the S domain, this would be -2, -10. Make sense? Connected, right? So if you observe something in root locus, based on this knowledge, you should observe the same idea in your body plot as well. You should be able to do that. So the break frequency for this would have been -2, and so omega would be -2, -10. We will call them omega TD, but we will see that shortly. So I'm just gonna say omega 1 and 2 for now. So you have 2 break frequency because you have 2 poles here. Now, back to lead and lag compensators. Do you remember the pair, what are like for S domain? Because S and frequency are connected. For S domain, how did you create the lead compensator? Okay. Pole and zero. So lag and lead, you put a pair, pole and zero. If you just add a pole, that's pole placement. That's a different technique. So for lead compensator, you add a pole and zero. Now, what's the relation between your pole and zero? Zero is closer to the imaginary axis. So you always have a pair, zero closer to imaginary axis, pole is farther. Both of them are farther from the imaginary axis altogether. Now for your lag compensator, you have it flipped, still a pair of pole and zero, both of them closer to imaginary axis. Now, from this knowledge that if a pole is close to imaginary axis, how does that controller is going to behave? So think of controlling things. If you put a pole near, so when we say control stability, even you're adding the zero, the pole is the one that is impacting the system, right? So a pole close to imaginary axis, what does it do? Think of system specification. A steady state error. It reduces a steady state error because it almost looks like an integral. If it was 1 over s and that pole was on the origin, it would get rid of the steady state for you, right? So a lag controller, because of that pole being close to imaginary axis, acts like a PI controller. So that's the thing. We talked about all of this before. What you need to do is connect the dot with the information you have. Like I have told you everything you need a few weeks ago. I'm repeating myself with different perspective, basically. All right. When you're studying, when you look at things, I want you to have this kind of perspective. What does it mean? What does that pole do near the axis? Now, for the lead controller, lead compensator, you're adding a pole farther. The dominant pole is like the pole is over there. So it's going to bring all the root locus and everything toward the left, toward stability. That is like making a system faster. And then because it's also adding more pole on the real axis, if you remember the relationship between beta and zeta increasing the damping, so it should act like adding some damping, making system faster. Which controller did that for us? PD controller. So this acts like PD controller. So if you needed to design a PD controller, you couldn't figure it out, or you had some other requirement in like frequency domain, you can go with PD. It would act like lead. Also in PD, you're adding a zero. There, you're adding a zero as well. So they have close relationship to each other. Everything else that we talked about them still applies because they're the same thing. All right. Now, more specifically, this is basically the summarization of what I just talked about. The poles of the closed loop system will go more toward the left, makes the system more stabilized, faster response. For designing a lead controller, if you had a requirement on phase lead, on phase margin, like our system has to have 60-degree of phase margin. If you had this requirement, you have to have the lead controller in your control system. Now, you could also design a lead lag controller, put them together. But if you had phase margin requirement, a lead has to be there. Your lag could take care of the steady state error for you, but the lead would help you with the phase margin. All right. And does not affect on the magnitude plot much because it basically adds that zero impacts the phase. And if you needed more than 70-degree phase margin, do you remember we said minimum we usually need 30 degrees, maximum we go 70. Now, if your system needed more than 70, you just add another lead controller. We call it double lead. So every lead would just compensate for 70-degree of phase change, right? Does anybody know the reason? Have that question, we'll get to it, please the answer. I have it in the slides. All right. Actually, it's right there. When you're adding a pole, you're going toward your higher frequency. When your phase is higher, what happens at higher frequencies? Noises, right? We don't like noises, so we don't want to be in the high frequency. We want to eliminate those. So that 70 comes from that. Like there's a equation, but you don't have to deal with that right now. Okay, designing a lead compensator, same equation as before. So your alpha is the ratio between 0 and pole. And you can design your controller. G of C is K times TDS plus 1, alpha TDS plus 1. Now, that TD and alpha TD are your break frequencies. Basically 1 over TD and 1 over alpha TD. So do you remember in lead compensator, was your 0 closer to origin or your pole? 0, right? Now looking at your body plot here, which one of these you think is the 0, the frequency of the 0? The first one, right? Because this is near the imaginary axis. So this is your 0. So your 0 is 1 over TD. Your pole is 1 over alpha TD. Omega of pole, omega of 0. So, which here is just omega. So those are your break frequencies. Breakaway. It's not breakaway, it's break frequency. Now, you can find alpha using the max phase lead you need. That's why lead control is good for meeting requirement for phase. So if you have a maximum phase lead, phi max, you put in that equation, you get alpha. Why is good? Why alpha is good? What does alpha tell you? Alexis, what is alpha? You can read from the slide. Look at here. Yes. So when you find alpha, you know what kind of relationship your pole and 0 can have. Because again, in designing control, you could pick any two pair. So your pair of pole and 0 could be different from his, right? As long as the ratio between them is correct ratio, you could choose them, right? It would be just different design. So but that alpha is important. So if you have a phase margin, phase lead requirement, let's say it has to be 50 degrees. So our phi max is 50. So 1 minus sine of 50 degrees over 1 plus sine of 50 degrees. Whatever that alpha is, that's the relationship between your pole and 0. Real part, real pole, real 0. So that's one thing. You also want to know what's that omega, at what frequency that happens. The relationship for that is 1 over t square root of alpha, or simply square root of the magnitude of pole times the magnitude of 0. Whatever that number is your frequency of your phi max. So you basically figured out your phase plot. You have the two frequency of your magnitude plot, the break frequency, so you can easily plot them. Right? So you can estimate your solution based on this information. Hence, you design your lead controller. That's all you need, alpha and TD, right? That frequency. Does that make sense? All right. Well, you need practice for this, but the fundamental, the equations, all that two simple equations. Example. What's the maximum phase lead for a lead compensator with a 0 at S-2 and pole as S equal to -10? Also find the omega max, at what frequency that happens. You can use the information from the previous slide. Zoom classroom, you put your final answer in the chat. So we need two things. What's the phi max and at what frequency that happens? Review, like maybe 2 minutes and I'll do it. I don't use it as a controller, I just need two values. Unit method. To save you from solving that equation. Okay, did anybody solve this? Sorry. Sine. Actually, let's solve that. So what is this? It's 0.5 divided by 1.5, right? So 1 minus alpha. Oh, I put 5. Sorry. That's why you don't do what I did. Plus 0.2. Okay, that's 2/3. 2/3. Okay. Okay, what's that in degrees? 41. 8 degrees. So that's your phi max, and this is the rate, the omega that it happens. So kind of this. So usually you have a requirement for your phi max, okay, and then you find alpha from that equation. Then you find a colon 0 based on that, and then omega max is just from there. It only depends on the location of pole and 0 or 0. Okay. So the design problem is really backward, but since you could have it in your final exam, you don't have access to MATLAB, so I'll go in this direction. I give you the colon 0 and actually find it. Okay. I could also give you a bunch of like colon 0s for a PM requirement. You just have to check. Okay. So when you're studying, put different values for 0 and pole and see if you can find the solution. All right. Okay. So as you increase the, so if you notice, alpha only depends on pole and zeros, right? So if you plot that, I will get to your question. Let me finish this first. So if you plot that, it will kind of saturate at -9 at 90 degrees, like 1 over alpha. That's why like we can get more than that from a lead controller. So we stay at 70 degree, and if we needed more than 70 degree phase, we would add another lead controller, because the ratio between 0 and pole is not going to give us more than 90 degree. And we try not to get to 90 degrees. 70 is where we're going to stop. So if we needed more than 90 degrees phase lead, we are going to say our controller becomes a double lead, TDS plus 1. You can even use the same controller, but like to the power of 2. So this is called double lead. So you don't have to find 2 different pair of 0 and pole. You could just raise to the power of 2. Okay, now what's your question? TD is not negative. No. Okay, this is like, because we don't have negative frequency, right? So it's 2 on the negative part of real axis. That's what it means. So when you come to the frequency, you already know negative frequency doesn't make sense. You just put the magnitude. All right. For phase lag compensator, again, you have alpha, the relation between pole and 0. You know that the pole is closer to the imaginary axis. You have the equation, and then the impact of lag is if you wanted to increase DC gain, get rid of a steady state error, and it will actually decrease the speed of the response. But if your system acting really bad at high frequencies, you could use a lag for it. If not, don't design a lag controller, okay? So if you have a noisy system, you can use a lag. So basically their equations are the same, right? The way you put your pole and 0 is different. So alpha is a different value. And they're both acting like kind of low pass filter type thing, right? Because they're trying to get rid of some of the frequencies and pass through basically some of the frequencies, right? You don't have to think about the relation between filter. I always like to mention that, but same equation. The difference is the alpha itself. We use them for different reasons. Get rid of a steady state error, lag. PM requirement, lead. If you had a design problem, these are the steps that you will go through. You'll find a K value. You determine the PM, like phase lead that you need for the project. You have the equation for alpha from that. Find your pole and 0. Find your omega max. Draw in MATLAB. That's why for design you need to have MATLAB. Look at your body plot. If it met all your requirements, you're good. If it didn't, you iterate. You just change the value of your pole and 0 slightly because you have the alpha, you have the relationship. They're just not quite right where you place them. You could use the toolbox for that and play with it. Now, the design example at the end of this lecture, basically going through this step by step, designing a lead controller. You need to review that on your own because your class participation is exactly that. But I want you to follow that and use the toolbox and everything. When you got your lead values or whatever this controller, put that on a MATLAB script, run the compensated system, show me the step response, body plot, and root locus, and tell me if you met the requirement. There is a requirement in the, okay? Same thing for lag. We usually design lead controller, not lag much, but if you ever need it, this is the process. Same thing, you pick the values and then you just iterate until you meet the requirement. Now, the difference between controller, why would we choose one versus the other one? So, you have a steady state error, use PI or lag controller. So a PI controller, if you are in frequency domain, can add a little bit of phase below the frequency point, improve SS errors. That's the big part. If you are using a PD because you have some phase requirement that you want to meet that requirement. If you use a lead lag, it acts like a PID controller because it has all the terms. All right, and then phase lead or phase lag on their own So a PI controller in frequency domain is basically a KP, a gain, plus, so your S here is 1/2, right? Yeah, so you have the frequency requirement for it. This is good for if you know what your system needs, what to pick. Same thing for your PID controller, the way that you choose PID controller, do that. Questions? Does the concept make sense? What I want is you should be able to follow this lecture on your own and understand everything that happened today. All right, so this is the end of this part. This is the root locus example from a few class lecture before that I've never actually went over. I'm gonna do that one for a quadcopter example that I don't think anybody solved it. But I already put the solution in today's module. I had an incomplete code before. Did anybody try to look at that or solve it? Okay, so that's the thing, it has to be an assignment. But what I was talking about, your class participation, this is your class participation. So you have a system, open loop, this is different from loop. This open loop means this is just your system. This is your G, open loop transfer function, G, okay? You are going to design a controller from lead or lag. These are your design requirements. Now, what I did is I actually did it for you, but I want you to follow us step by step, do all of those on your own on your computer. When you get to the end, when you get here and you have all the values, you write a MATLAB script with this controller and show me the compensated values that you are meeting this, right? It's basically studying, implementing. That's all. You're not doing anything. You're not changing anything, basically. But this will help me to make sure you went through it at least once. Make sense? Good? So Monday, 3 p.m. by class time, submit M file and PDF publish with all the plots. Yes.
That means we're not writing it into a code, we're literally writing our command line to make this controller.
Oh, because when you are doing it, you can't write in the command line and do all the stuff on the tool, then you have to write in your script. So you create it in the script and everything. So the other way is create in the script, run, and then go to the system. You can do that too. So tutorial, then a script. I didn't give you the script. You have to do it yourself. All right. Now, go to your MATLAB. And I have the code, so you can actually download the code and so this is the code. Well, what? The code is locked. This page is locked. I could do it. It's unlocked now. Why am I doing this? I already have it. Well, I'm gonna show you why I do text, because you can easily move it to your MATLAB. So the question is saying that we have a transfer function between a pitch control input and a pitch angle for a quadcopter. So it's a pitch control, and pitch is the position, right, of the quadcopter. And we have some requirements. So we have the transfer function, and the desired system specification are omega n has to be greater than 1 radian per second, and your zeta has to be greater than 0.44. We have the block diagram, and then we are going to Design a control that meets this requirement. Now, theta s over t is 1 over s squared plus times actuator. So your plan times actuator is the quadcopter thing. All right. So let me clear that. Oh, I'm not sharing it with Zoom people. Yes. So we are going to create our quadcopter system. So the body and the actuator, 1 over s squared plus the actuator. And let's plot root locus and see what does it look like and what should we design. So this is your root locus. What can you tell me about this system? Is this system going to be stable for all gains? And what are other requirements? Are we meeting all of them or not? We can also plot our step of system G1. I'm going to tell this is 2. All right. Yes, I mean figure 2. You're doing it, right? You're just looking at what I'm doing. Like, I'm going to show you what you should have. You should be doing it yourself. Okay, so is my system stable? No. So what can I say from root locus about this system? Someone? Yes. So if you choose again, so this system is unstable when the lock keys are on the right-hand side, right? So there is a K that if you choose above that, the system becomes unstable. How can we find that? If we click on the root locus, it will tell us for that frequency. So I'm not close to 0 yet. So again, above this value, so if I keep going to get to 0, if I can move to get to 0, I should be able to get that K. If I can find that K, I know that anything more than that number will increase the instability. You see that already that K is pretty small, right? So let's design a lead controller, a lead compensator for the system. If I put a 0 at -1 and a pole at 10, the relationship is going to be what? The alpha for lead controller. It's gonna be 0.1, 0 over a pole, right? So you have your alpha. So if this number didn't work, you know what the alpha is. So if I design a controller, lead controller, so your lead controller will be like this. If I design that, then apply that to my system. Let me change the axis so you can see everything bigger. All right. So what happened is I changed the shape of my root locus first by adding a pole and 0. I still don't know if I'm meeting the requirement for zeta and omega n. How do I find that? How can I check that requirement? You have the code, you don't have to look up there. Read the stuff in the code. So I'm assuming nobody looked at the lecture that had using system control design and how we check omega n and zeta from. So do you remember if you click that, you could set design requirement. You have damping ratio that has to be, what's the damping ratio requirement? 0.44. Then click again, design requirement. There was another one. Is it natural frequency? What's that? 1. So is it minimum 1? Yeah, so it has to be greater than 1, right? So the white area is the area that you can put your compensator. So the part of this root locus that will be on the white, in the white part is your answer. So if I want to add a compensator, so edit compensator. So you need to add a 0 and pole for your compensator, right? We found what number we wanted to try in the code. What is the first one I tried? -2 and what? After I created my system, I said we need the lead. Let's say we want to design a lead controller. Currently, the system is not meeting the requirement. Then I said, what is your lead control? What is the location of pole and 0 there? So -1 and so pole 0 at -1, right? So you add a 0, real 0, and so I'm going to choose around here. I'm able to fix it. And then if I go to edit compensator, here, real pole location actually should be -1. So if I change that to -1, it's changing the shape of root locus. Now I have to pick a pole as well, right? To make it a lead controller. Now, what was that number? -10. So I'm gonna just pick here and I'm gonna go edit because so, -10. This is my new lead lag controller. All right. C value. So if you click on C, you can change your compensator gain. This is your lead controller part. And if you needed to add some gain, you can add here, yes. Oh, it didn't get added. Make sure this is, yes, thank you. Okay. So the pole, the 0, the pole you added, here is what your gain margin, here is your phase margin. So if you have phase margin requirement, you can check here. And the system is going to be stable. Now we have to check our other requirements to see if it's met or not. Now, design requirement, no, in target. Are you able to do that on your own, like right now? So this is the way that you will create your lead controller. Then you look and say, oh, my requirement not met. Find your Z done, oh my God. Then you change the value of pole. So you already created the compensator. You right click on root locus, edit the compensator, right? Change it to a different value. And then look at your response. And then again, from there, you will tune. So this has to be iterative process going until your requirement are met. So if I had, I don't know, some sort of overage requirement, I could check that. Now, you remember that you could also just move them, right, manually, and you get your system. Like, maybe I should go that way. Then you can see you're moving, let's say here, and you see the impact of your new pole and 0 on your system. Whenever you click on them, you can see what are the value for location of pole and 0 down on the bottom. So you can use this dragging to help you tune your lead controller. Same for lag, just the location of pole and 0 is different, right? So the lecture that we have an example for lead controller, follow that. You'll be able to do this one. And from this, you'll be able to understand your cost participation better. All right, because if I go over all of that and you don't do it, it doesn't matter. Like you won't learn it. You have to do it yourself. Okay. Friday is hitting hard. Okay, I'll see you on Monday. So yes, there is a password. Of course, there's always a password.